Rates of change examples. Alright, let's look at this example with multiple parts. Let x of t equal t cubed minus 3 halves t squared minus 18t plus 30. And that's going to represent the position of a particle that's going to travel along the x-axis, where t is given in seconds, and x of t, the position, is given in inches. For part A, find the position of the particle at t equals 1 second. So I'm interested in finding the position, and I'm given the position function. So if I want the position at time t equals 1 second, and t is in seconds, I need only substitute 1 into t into this equation, and that will give me my position in inches. So for part A, I'm interested in x of 1. So I'm going to plug in 1 everywhere there's a t, so 1 cubed minus 3 halves times 1 squared minus 18 times 1 plus 30. And I'm going to skip the arithmetic here and tell you that this is 11.5 inches, because remember that x of t, so x at any time, is given in inches. So now for part B, I'm asked to find the velocity at time t. So I'm given the position function s of t. To find velocity in general, right, this is at just some time t, I need to take the derivative of position. So v of t is equal to x prime of t, so the generic derivative of position. And this is nice because we can just apply the power rule. So x prime of t is 3t squared minus 3t, when I bring that 2 to the front, it'll cancel with the 2 on the bottom, minus 18. So there's my velocity function, and I should include units. So my velocity is a rate. So the rate is going to be in inches per second. So this quantity over the time. Alright, so part C, scroll down a little. Part C, what is the velocity after 2 seconds? So now I have this velocity function in terms of t. So for part C, what's the velocity after 2 seconds? All I'm being asked to do here is substitute the 2 into my velocity function. So 3 times 2 squared minus 3 times 2 minus 18. And skipping the arithmetic again, I'm going to get negative 12. And my units are velocity, so inches per second. So now let's move on to part D. When is the particle at rest? So in general, it's when is the velocity, v of t, equal to 0, when a particle is at rest. So v of t is this function here, so 3t squared minus 3t minus 18 equals 0. So to set this equal to 0, I'm going to have to factor it. So let me go ahead and pull the 3 out that's common in everything. So 3 times t squared minus t minus 18 equals 0. So this part right here will factor to 3 times t minus 3, t plus 2 equal to 0. So now I set each part with t's equal to 0. So sometimes students want to set 3 equal to 0, but that wouldn't make sense, right? Because 3 can never be 0. So I'm going to set t minus 3 equal to 0. So t equals 3. And then t plus 2 equal to 0. So t equals negative 2. Now let's keep in mind the units here are in seconds, so one of these should very obviously not make sense, which is t equals negative 2, because I can't have negative time. So this is not an answer. So I wouldn't take the absolute value of it. I would just ignore it entirely. I cannot have negative time. So in answer to when is the particle at rest, the particle is at rest at t equals 3 seconds. So at 3 seconds, the particle is at rest. Alright, so now let's move on to part E, and we needed some more space for that. So when is the particle moving in the positive direction? So for part E, an object is moving in the positive direction when v of t, the velocity, is greater than 0. So the velocity function right here, which was 3 times t squared minus 3t minus 18, I want to know when that function is greater than 0. So one of the easiest ways to solve this problem is to be able to graph it. So we already did a lot of the work when we factored it to be 3 times t minus 3 times t plus 2 is greater than 0. So what we just did was we found the x-intercepts. So if I were to graph this function, I know that one of the x-intercepts is negative 2 and the other is 3. And I know that the y-intercept is negative 18. And because this is a quadratic, it's going to look like a open upwards parabola because my leading coefficient is 3, it's positive. So it's going to look something like this. Now, it's very important to know that although this is the generic derivative function, the velocity, I'm only considering portions of this graph to the right of 0, because remember that the horizontal axis is time in seconds, and I can't have negative time, so I don't care about what's happening at all over here to the left. So I'm only interested in the portion of the graph over here on the right side. And what we're asking here is, when is velocity greater than 0? So this is my velocity graph. This is v of t. I just graphed v of t. So when is this parabola greater than 0 is like asking, when is this graph above the x-axis? So this graph, just to use one more color, is above the x-axis whenever x values are greater than 3. So this x coordinate was 3. So from 3 to infinity, open at 3, because I want to know when this is strictly greater than 0, from 3 to infinity, this velocity graph is greater than 0. So when is the particle moving in the positive direction? Well, first we have to know that that means when velocity is positive, when velocity is greater than 0. The velocity function is this quadratic. And how do you set a quadratic greater than 0? So the easiest way to do this would be to graph it. And then we're understanding conceptually that time has to be positive, so I only care about what's happening to the right of the vertical axis, so to the right of 0. And then this is understanding how to read a graph and when a graph is positive or above the x-axis. Alright, now let's work on part F. Find the acceleration at time t. So acceleration is the derivative of velocity, so a of t is v prime of t. So v prime of t, well, let's go back. Here's v of t right here, 3t squared minus 3t minus 18. So the derivative of this using the power rule is just 6t minus 3. And now my units of acceleration are going to have to be inches per second squared. So my units of acceleration have a time that's squared. So now for part G, when is acceleration positive? So when is a of t greater than 0? So a of t is 6t minus 3. So when is this greater than 0? Because this is a linear function, this one's easier to solve than one is a quadratic greater than 0. So 6t minus 3, we can solve this analytically by adding the 3 to the other side, dividing by 6. So this is when t is greater than 1/2. So an interval notation from 1/2 to infinity. So acceleration is positive for time values from 1/2 to infinity. So this was a time interval as well. So this is t time in 3 to infinity, and this is time in 3 to infinity or 1/2 to infinity as well. So for part H, when is the speed of the particle increasing or decreasing when t equals 2 seconds? Sorry, this when shouldn't be here. The question is just, is the speed of the particle increasing or decreasing when t equals 2 seconds? So hint, when v of t and a of t have the same sign. So is the speed of the particle increasing or decreasing? We need to see what's going on at v of 2 and at a of 2. If they both have the same sign, then the speed is increasing. If they have opposite signs, the speed is decreasing. So v of 2 we actually already found in part C. So v of 2 is negative 12 inches per second. And a of 2, so we could, if we want, just go ahead and plug 2 into a of t. So that would give me 6 times 2 minus 3. So that's going to give me 12 minus 3, which is 9. So this is positive, so 9 inches per second squared. So velocity is negative, acceleration is positive 9, so the speed is decreasing. But in fact, we actually didn't even have to plug in 2, because in part G, we found that whenever time is between 1/2 and infinity, the acceleration is positive. So 2 is in this interval, so we knew that a of 2 was going to be positive. But substituting in 2 was okay, and we already had v of 2 from part C. So since velocity is negative and acceleration is positive, speed is decreasing. And we would want to write that since a of 2 is greater than 0, which means positive, and because v of 2 is less than 0. So we were at the point where we need to justify our work, so this right here is the justification. Alright, so we now have to work on part I, and part I is going to take a little bit of thinking about. Find the total distance traveled by the particle during the first 3 seconds. So first I want to go back and think about that man that was walking on a horizontal line for a second. So he started out at the origin or at an initial location, and then after 10 seconds had passed, he traveled 8 meters. So 8 meters in a total of 10 seconds, and this is where he ended up. And then he stopped. And then some time passed, and then he turned back and went 4 meters back toward where he was in the first place, and that took a total of 4 seconds. So if I wanted to know, let's just say that was the end of the path, so he ended up back right here. So if I wanted to know the total distance traveled, well, I would have to know how far he went from 0 in the first 10 seconds, so that was a total of 8 meters. And then he stopped, and then he went backwards, and so I'd have to know how far he traveled from when he stopped to that next 4 second, over that next 4 seconds for a total of 4 meters. So I would have to add 8 meters and 4 meters together. But the key is where he stopped. So I would need the distance from, let's call this time 0 to time 1. So I would need that distance from time 0 to time 1. So that would be s of t1 minus s of t0. So I need that distance between those original times, but then I would also need to add the distance from traveled between time 1 and time 2. So the distance between time 1 and time 2 is s of t2 minus s of t1. Now we want our distance to always be positive, so what we're going to do is we're going to take the absolute value of both of those quantities, and then we add the two distances together. So the distance between time 0 and time 1, that was 10 seconds in that example, and then or not 10 seconds, I'm sorry, 8 meters. And the distance between the time 2 and time 1, the distance traveled was 4 meters. So this would have been a total of 12 meters. So that's just a modification to that first example, but the key is we needed to know where the man stopped and the two times that we would have to find the distance between. So if I want to know the total distance traveled by the particle during the first 3 seconds, I need to ask myself whether or not this particle stopped during the first 3 seconds. Because if it started at an origin location and then moved to the right and then stopped sometime between 0 and 3 seconds and went back, I would need to add up more than one distance. So we actually answered the question of when was the particle stopped in part D and when is the particle at rest. So it turned out that the particle was at rest at 3 seconds. So that was the first time the particle stopped, was at 3 seconds. So in order to calculate the distance, what I would need to do is just find the position at 3 seconds, so what's s of 3, and subtract the position at time 0. So where I ended up after 3 seconds minus where I started at time 0, and take the absolute value of those two locations, those two positions, and that will tell me how far I traveled. But if I had stopped somewhere between 0 and 3 seconds, then I would have to break it up into more than one interval. So I would have to break it up into different positions because there would be different amounts traveled over different time frames. So I would go back and think about that example of the man walking to think about the total distance traveled. We would have had to add his forward direction distance to how far he went in reverse, and then he ended up actually going back forward again. So we would have had to add up a total of 3 quantities to figure out the total distance traveled for that original man walking in a horizontal line. So for this one, because the particle actually just stopped at 3 seconds, all I need to do is find s of 3, the position at 3, minus s of 0. So in other words, I need to plug 3 into the original function. So, sorry, these should have been x's. So x or s is typically used for position. So x of 3, so I need to do 3 cubed minus 3 halves 3 squared minus 18 times 3 plus 30. and that whole quantity minus substituting in 0. But that's kind of nice. If you plug in zeros everywhere for the t's, it's just really going to be minus 30. So this quantity is the absolute value of negative 40.5, which is just positive 40.5. So the total distance traveled is 40.5 inches during the first 3 seconds. Alright, in this first example, we have the position of a particle is given by s of t equals t cubed minus 3t squared minus 6t plus 5, where time is measured in seconds and s of t is measured in feet. In part A, we're asked to find the initial velocity. So again, initial is a keyword meaning that time is 0. So in other words, find the velocity when time equals 0. So first we need the velocity function, so we're going to need to take the derivative of position. So v of t is 3t squared minus 6t minus 6 using the power rule. So the initial velocity v of 0, if I substitute 0 into each of these t's, the only thing left over is going to be negative 6. And it's important I include units, so feet per second. Now in part B, find the velocity after 2 seconds has passed. Now I'm going to have to substitute 2 into my velocity function. So I'm interested in v of 2. So 3 times 2 squared minus 6 times 2 minus 6. So 2 squared is 4 times 3 is 12. Minus 6 times 2 is 12. Minus 6, so 12 minus 12 is 0. So I get negative 6 again. So I haven't introduced this image yet. This image represents the position. This is s of t. So this is t cubed minus 3t squared minus 6t plus 5, graphed out on an xy plane. So the units or the labels are incorrect here. This should actually be my time axis, where time is in seconds, and then the vertical axis is going to be in feet, because this represents my s of t, my position. So what we just found in part A, v of 0, the initial velocity. So at time 0, the slope of my tangent line, because if I want velocity or instantaneous velocity at time 0, the slope is actually going to be negative 6. So if at 0 I drew a tangent line, the slope would be negative 6. And what we just found is that at time 2 seconds, so at 2, if I were to go to the function and I were to draw myself a tangent line, that would also have a slope of negative 6, coincidentally. And now in part C, find the acceleration after 2 seconds has passed. Well, I need the acceleration function. I need a of t. I need the derivative of velocity. So the derivative here would be 6t minus 6. And then we can just go ahead and substitute in 2. So a of 2, so 6 times 2 minus 6, 12 minus 6 is 6. And then my units are going to be feet per second squared. Alright, and that's it for the first one. So negative 6 feet per second, negative 6 feet per second, and then positive 6 feet per second squared. Alright, number 3, and the GC just indicates that we would probably need our graphing calculator on this problem. If a stone is thrown vertically upward from the surface of an unknown planet, its height in meters after t seconds is given by h of t equals 10t minus 0.5t squared. Part A. What is the velocity of the stone after 1 second? Second, not seconds. So after 1 second, I'm interested in finding the velocity. So this is a position function. This tells me about the height or the location. So I need to find the velocity function. So v of t is going to be 10 minus, so this is 0.5. So if I multiply 0.5 or 1/2 times 2, I'm just going to get out 1. So the velocity function is just 10 minus t. So the velocity after 1 second, v of 1, is 10 minus 1. So my velocity is 9 meters per second. Now in part B, what is the velocity of the stone after it has risen 18 meters? So this is kind of a tricky question. What is the velocity of the stone? So I want a velocity just like in part A, but after it has risen 18 meters. So in this previous one, I wanted the velocity at 1 second. And I could go ahead and substitute that time of 1 second into my t of my velocity function. But here I can't take 18 meters and substitute it into my time. So what I have to do is find the time when the stone is 18 meters high. So I'm going to go ahead and do part B over here where I have some space. So what I first need is a time to substitute into the velocity function. So to find that time, I want the height of my stone to be 18. So what I'm doing is I'm going to have to set 10t minus, and I'm going to write this as 1/2 t squared. I'm going to have to set this equal to 18 and solve for t. Now, here's what I cannot ever do, is just go ahead and take a t out of both of these parts and set each one equal to 18. That is not how I solve a quadratic. So what I have to do is get everything on one side and a 0 on the other side. So what I'm doing is I'm going to put the negative 1/2 t squared first, the 10t next, and then I have to subtract 18 over to force this to equal 0. So I cannot, again to repeat, I could not at this step just pull out a t and then set each piece equal to 18. That does not ever work. I have to set the function equal to 0 and then factor. So instead of dealing with fractions, what I'm going to do is multiply both sides of this equation by a -2 to get rid of my fractions. So -2 times negative 1/2 t squared plus 10t minus 18, and then -2 times 0. So that will keep my right side 0. It'll just leave me with something easier on the left side to deal with. So this is going to be t squared minus 20t plus 36. So now what I want to try to do is factor this. So now that my leading coefficient is a 1 right here, this will factor to t minus or plus something, t minus or plus something. So I want two numbers that multiply together to give me 36 and add together to give me -20. So -18 and -2 will work. So if I just check this out, this will be t squared minus 2t minus 18t. That gives me minus 20t. And then -18 and -2 is 36. So now I can set each of these equal to 0. So t is 2 and 18. Alright, so now let's go ahead and think about this for a second. What is the velocity of the stone after it has risen 18 meters? So now let's take a look at this picture for a second. This is my h of t function graphed, where t is in seconds and my h of t is in meters. So this is kind of a tricky question because I want to know the velocity after the stone has risen. That's why it's italicized, 18 meters. So it turns out that this stone that's thrown up is going to cross 18 two different times. So it's going to start out on the surface of the planet, so that's down here at 0. And then the stone is going to rise up, and that's when the first time it's going to hit 18, we just found out, is 2. So right here at 2, that's the first time that the stone's going to reach a height of 18 meters. Then it's going to keep going up. It's going to reach its maximum height, and then it's going to turn around and come down. And it looks like at 18, it's going to reach that height of 18 again. So the time that I'm interested in, although there are two times when the height of the stone is 18 meters, I'm interested in when the stone has risen 18 meters. So I'm interested in time 2. So now what I do is I substitute 2 into my velocity function. So v of 2 is 10 minus 2, which is 8 meters per second. So what is the velocity of the stone after it has risen 18 meters? So the slope of the tangent line there is 8. So 8 meters per second is the velocity of the stone at 2 seconds, or at the first time it hits 18 meters. So in part C, when does the ball hit the ground? So let's take a look at the graph and see if we can think about that intuitively a little bit. If the ball is on the ground, then its height, and this is its height function, would have to be 0. So we have to pay close attention to the wording. When does the ball hit the ground? Well, the ball is on the ground at time 0 when it started, but the ball is going to hit the ground when it comes and finally turns around and lands on the ground. Over here at what looks like 20. So we'd have to actually solve this out. We couldn't just look at the graph because, again, the graph wouldn't be given. So when does the ball hit the ground? That's when the height is 0, right? That's when I want to know when the ball's on the ground, is when the height is 0. So here I'm going to set h of t, that I'm going to do that over here because I'm running out of space. H of t equals 10t minus 1/2 t squared. When does this equal 0? So notice that this is already set equal to 0. So like on this one, I had to move the 18 to the other side. This one's already set equal to 0. So I can factor out the t from this side. So if I factor out the t, I'm left with 10 minus 1/2 t equals 0. So now I set each piece equal to 0. So 10 equal to 0, and then 10, or t equal to 0, and 10 minus 1/2 t equal to 0. So if I subtract the 10, so negative 1/2 t equals negative 10, and then multiply both sides by negative 2, I am going to get t equals 20, which is apparent from my graph. So when does the ball hit the ground? T equals 20 seconds. And then finally, part D, what is the speed of the ball when it hits the ground? So we just found the time when the ball hits the ground, so now I want the speed of the ball when it hits the ground. Now speed is the absolute value of velocity. So what I'm setting up here is the absolute value of v of 20. So whatever the velocity is at 20 seconds, and then I take the absolute value of it to find the speed when the ball hits the ground. So v of 20 is going to be the absolute value. My velocity function is 10 minus t, so 10 minus 20. So the absolute value of negative 10 is just 10, and my units are meters per second. So what is the speed of the ball when it hits the ground? When a ball hits the ground, its height is 0. The time when that happened was 20 seconds, and then we just had to make sure to take into account that it's speed, so it's the absolute value. Alright, example 4. The position of a particle is given by the equation s of t equals t cubed minus 6t squared plus 9t, where t is measured in seconds and s in meters. Part A. What is the velocity after 2 seconds and after 4 seconds? So I need the velocity function. I need v of t. I'll go ahead and put that up here. So the derivative is 3t squared minus 12t plus 9. So I need to substitute 2 and 4 into that velocity function. So v of 2, skipping the arithmetic here, is negative 3, and my units are meters per second. And v of 4, if I substitute 4 into each of those t's, I'm going to get positive 9 meters per second. So let's go ahead and take a look at the graph now. This would be the position function s of t. So the vertical axis units are meters, and the horizontal axis is seconds. So what we just found is that at time 2, if I were to draw a tangent line, that instantaneous rate of change, that velocity, is going to be negative 3. And at 4, if I were to go ahead and go up to the graph, maybe way up here, and draw a tangent line, that instantaneous rate of change would be 9 meters per second. So now in part B, when is the particle at rest? So the particle is going to be at rest when velocity v of t is set equal to 0. So let's go ahead and look at our graph for a second and think about how many answers we're going to get out. So if the velocity is 0, well, that's like saying the derivative of position is 0. So I can see on this graph that there's going to be 2 places with horizontal tangent lines. One clearly looks like 3, and the other looks like probably 1. So we're going to actually have to do the work to show this. We're going to have to set the velocity function. So I'm going to continue that work up here. 3t squared minus 12t plus 9, I'm going to set that equal to 0. So I'm going to go ahead and factor out the 3 and have t squared minus 4t plus 3 equal to 0. And then I'll have to factor this to be t minus 3, t minus 1. So as it looked like in the graph, t equals 1 and 3 are the 2 times in seconds where the velocity is 0. So that's when the particle is at rest. So at 1 and 3 seconds. So again, I would not be given the graph, so this would be the way I have to solve this. Now, just to be clear again, I can't move the 9 to the other side, make it negative 9, factor out the t's. That doesn't work. Whenever I solve an equation, I have to have one side be 0. It's the only way it will work. So now in part C, when is the particle moving forward? So what I'm interested in is when is the velocity greater than 0? When is the velocity greater than 0? So that's like asking, when is the derivative positive? So if I'm able to look at the graph here, well, for one, I'm only concerned with what happens to the right of this vertical axis, so 0 and on, because over here this is negative time, so that doesn't make any sense. So from 0 on, I'm thinking about when is the derivative positive. So I'm thinking I want positive slope. So we would have to solve this without using a graph. But if we had a graph like this, the particle is moving forward when the graph has positive slope or positive derivative values. So between 0 and 1, if we just found out this was a maximum up here, this is a place where the derivative is 0. Over here, if I drew a bunch of tangent lines, they would have positive slope everywhere. So the particle would be moving forward between 0 and 1. And then all of a sudden between 1 and 3, I start having negative slope. As we found at 2, I had negative, negative, negative slope. So I don't want that to be part of my answer. But as soon as I get past 3, I start to have positive slope again. This was positive 9. This would be positive slope. All of this would be positive slope. So 0 to 1, and in math, this U means and. 3 to infinity would be my answers. Now, I would have to, again, solve this analytically, or I would have to do it by setting the equation up here, 3t squared minus 12t plus 9, to be greater than 0. But really, that's going to translate to graphing this quadratic and looking at where it's above the x-axis. So if I pull out a 3, and I'm going to write down the factored version already, so 3 times t minus 3 times t minus 1, when is that greater than 0? Well, I'd have to graph this thing and know that 1 and 3 are my x-intercepts, or my t-intercepts. And this is going to be a parabola, because it's t squared, with a positive leading coefficient, so it's going to have to open upwards. I don't know exactly what it looks like, but I just need a sketch. So it's going to open upwards, and again, I'm only concerned with what happens from 0 and to the right. So when is this graph greater than 0? Means positive, or above the x-axis. So this graph is above the x-axis, from 0 to 1. Use a different color. So from 0 to 1, this graph is above the x-axis, and then from 3 to infinity. So I read my answers from along the x-axis. So from 0 to 1 and from 3 to infinity, this graph is positive, which means that's where the derivative is positive, and I need the derivative to be positive to know when the particle is moving forward. So now, in part D, is the particle speeding up or slowing down at 2 seconds? So if I want to know when an object is speeding up or slowing down, I have to know the velocity at that particular time and the acceleration at that time. So the velocity we already found in part A was -3 meters per second. So now I need the acceleration at 2. So up here under velocity, I'll go ahead and write the generic acceleration function in terms of t. That's 6t minus 12. So if I plug in 2, 6 times 2 is 12, minus 12 is 0. Now 0 is neither positive nor negative. So in order to say something speeding up or slowing down, both acceleration and velocity have to have the same sign or opposite signs, but 0 has no sign. So at 2, the answer is neither speeding up or slowing down. Neither speeding up or slowing down. It's not doing either. And now for part E, so I'm going to go ahead and scroll down and make a little bit of space. So find the total distance traveled by the particle during the first 4 seconds. So I need to know whether or not the particle stopped at all during the first 4 seconds. And in part B, we know that it did. The particle stopped twice during the first 4 seconds, at 1 and at 3. So what that means is I'm going to need to add up all of the distances traveled over each of those intervals. So let me write out the expanded version and then we'll talk about it. I have to figure out how far the particle traveled between time 0 and time 1 in the distance function or the position function. So I need to know, well, where was the object at 1 second, and subtract where it was at 0 seconds. So the absolute value of s of 1 minus s of 0. So the position at 1 minus the position at 0, that's how far it traveled between 0 and 1 second. Then I need to add to it how far the object traveled between 1 and 3 seconds, the next time it stopped. So it stopped at 3. So where was it at 3 seconds? What's S of 3? And then I'm going to subtract where it was at time 1. So this is how far the object traveled in the first second. This is how far the object traveled over the next 2 seconds, from 1 to 3. And then I need to go up to 4 seconds, so I need to add, well, where was it at 4 seconds minus wherever it was at 3 seconds. So I have to add up 3 total distances to get the total distance traveled. So this would actually be a lot of tedious work in algebra, because what we're doing is we're going to plug 1, scroll up just a bit, plug 1 into S of t, plug 0 into S of t, plug 3 in, plug 1 in, and add up all of these different quantities. So in the interest of time, I'm going to tell you the answer. This is the absolute value of 4 plus the absolute value, this happens to be negative 4, and this one happens to be positive 4. So this would be 4 plus 4 plus 4, so a total distance of 12, and my units are in meters.